Hi everybody, welcome back to Chiptorials. I'm Dylan, and today we're going to be talking about motors. Motors can get pretty noisy without the proper timing or control, so just moving a motor a couple of degrees can be a really challenging task. When your motor's too noisy or it isn't consistent, it can really take away from your great designs. So today we're going to be talking about motor commutation, or the process of switching phases within a motor. Effective motor commutation can vary depending on the application, so that's why it's important to know the different types. Today, we're going to be focusing on BLDC motors and the two main types present within those systems, trapezoidal and sinusoidal. They get their names based off the waveforms they generate, so sinusoidal will produce a smooth sine wave, and then trapezoidal is more of like a ramped square wave. We'll get more into what those look like in the next examples I have coming up. Trapezoidal motion is more powerful than sinusoidal. It's also less complicated, it takes more energy, but it also outputs a lot more torque. This is because we're driving the coils of the motor to the highest and the lowest bounds of energy. This type of usage actually causes a feedback, and you can hear it from the motor, a sort of hum or a screech. Now let's take a look at the waveform and listen to the motor. I have it all hooked up. Let's take a look at the waveforms and also pay attention to the motor operation itself. Pretty noisy, huh? Now let's take a look at this logic analysis. So every waveform you can notice is an actual trapezoidal waveform. This is where the commutation gets its name, and it will be different for the sinusoidal as well. Now let's talk about sinusoidal drive. Sinusoidal, when compared to trapezoidal, is less powerful, but that doesn't mean it doesn't come without its own benefits. For instance, sinusoidal drive is a more efficient and, more importantly, it's a way quieter way of driving BLDC motors. And this is because of how it's actually powering the motor. When you look at trapezoidal, you're going from an instantaneous 0 to powered up. 0 to powered up versus sinusoidal, you're actually following that sine wave. So it's from 0 to a gradual power up, and during that entire time, the motor coil is actually being powered up. It's allowing the rotor to actually partially rotate, and it allows for a smoother transition and slower speeds. Let's take a look at the waveform and let's listen to the motor too. Now that we have our board all set up, let's take a closer look at sinusoidal commutation. And let's try to compare this with our trapezoidal application by looking at the logic analysis and the motor performance as well. One thing you'll notice right off the bat is this is a much quieter motor. This is because of the sinusoidal commutation and its efficient use of power. Let's get more into it by looking at the waveforms. So above here we have our digital signals and our analog representations below. Looking at the digital signals of our PWM, you'll notice that we're never completely off and we're never completely on either. This is what gives sinusoidal commutation its benefits. Because of this, we're actually giving it a gradual increase of power. And even when we're at our max, we're still giving it more and more by varying that duty cycle and giving it a bit more of a time on than time off. When we get to our max, we start regressing back down, and eventually that coil powers off. And we do these with all three phases. This generates a partial rotation, a more quiet turn, and a more efficient use of the motor. Whether you're new to motors or an experienced user now looking for an efficient and optimized solution, Microchip has introduced a new product for motor control, the AVR EB. This product has two new peripherals, Timer Counter E and Waveform Extension. The Timer Counter E is a new timer peripheral designed specifically for motor control timing, offering 4 output channels that are ideal for BLDC and stepper motor control. The waveform extension further enhances this capability by enabling dead time insertion, blanking, complementary waveforms, fault detection, and pattern generation. The EB is fully enhanced with the multi-phase power board. This is a motor control board that can handle from 6 to 50 volts, comes with an assortment of hardware peripherals, and plenty of ICs to help regulate temperature and current. For a full list of these, be sure to check out the user guide. This board also acts as a reference design, so the user guide is actually full of a lot of useful information like schematics, part lists, and board-specific calculations. In addition to all of this, we also offer a BLDC motor control library on MCC. It's free, it's ready to integrate into your projects. This library even comes with API, motor, and board settings, even example demo just to show how to get a motor moving out of the box. Let's get into these libraries and how fast it takes from opening MPLAB X to motors in motion. So I just made a new project and I have MCC open. I have all my files updated. If you don't, there's a nifty little button right here, the Content Manager. This will allow you to easily edit your files you have for MCC. So if anything's not too up to date, you can find it, and very fast too. This will update if you don't already have the motor control libraries. That's where you should be looking. So let's get into it. The motor control libraries themselves are right here, and all you got to do is press that green little button. It'll take a second, and then bam. It's already added in. So from here, we get a couple of settings. So general, motor specific, startup. So there are a couple things that you can just change depending on your application, or if you have some specific timing measurements in mind, you have all the options too. For more basic general settings, up at the top, you have the choice between censored and censorless, and trapezoidal and sinusoidal. The sinusoidal is only for the censored option though, but it is right there if you want to look at it or check that out as well. For right now, I'm going to keep it at trapezoidal and censorless. And we have other options too, such as pole pairs, phase advance, motor startup. The more important one here is the phase advance. This is one of those settings that if you're having a problem with your motor, this is the one that you want to check out first. I'll put a link in the description for the motor control library user guide and also the GitHub. It has plenty of information on what these settings do, how to change them up, and also how they impact your motor performance. So aside from this, it looks like all my settings are good, and I'm going to run with them. Now, let's look at some of our warnings and hints we get from MCC. Me personally, I'm going to have to take a look at the interrupt manager and then also the clock control too. So we go here, clock control. Clock control. We disable the prescaler, and for our interrupts, we just make sure that they're enabled. From there on, we're able to generate new file, generation complete, and we have a project that's ready to implement. With that project we just generated, I'm going to program it and show you the results. Program complete, and we now have a motor that spins. And we also have a potentiometer to control the speed. If you're interested in any of the material we talked about today, or maybe you just want to get some products on hand for yourself, I'll be putting a link in the description for everything, for the AVR-EB, the adapter board, and the multi-phase power board. If you're wanting to get more into the EB and just getting started with TCE and WEX for motor control, I'll also be providing links for our GitHub and our Discover, which has the most up-to-date code examples for the AVR-EB, and we have some examples pertaining to BLDC, stepper motors, and even just getting started with the peripherals themselves. If you want even more than just that, we have a real-life, real hardware example on Microchip Try. Microchip Try is a new service we're providing where you get to see a real-world example and you actually get to change some environmental factors with it. For the AVR-EB, we have one where you get to see a motor spinning, but you get to change whether it's trapezoidal or sinusoidal commutation, and you also get to change the speed yourself. I think it's a really cool one, and you should definitely check it out. And if you have any other questions, be sure to leave them in the comments.